Hello and welcome to lesson 1.6, L'Hôpital's rule. So, what we've seen in the past is we can calculate some limits using algebraic tricks that we can use to evaluate if they're in indeterminate form. But some of these tricks don't actually work for all these kinds of expressions. So we're going to find one other rule that we're going to learn today that'll help us out, and that's called L'Hôpital's rule. So remember that we tried to calculate the limit as x approaches 0 of sine x over x before, with the function specifically y equals sine x over x. Well, the only way we could do this is if we could actually graph this thing. And when we tried it last time, we just found out it was equal to 1, and I told you, unfortunately, just to memorize it for the time being. Well, today we're going to learn how to do that. So, L'Hôpital's rule, spelled hospitals, but le hospitals actually, but it is pronounced l'hôpital. It's French. So suppose that a function f of a is equal to g at a is equal to 0, or f at a equals g at a equals infinity. That f and g are differentiable on an open interval I containing that value a, and that g prime at x does not equal 0 on that interval if x doesn't equal 0. Then what we can state is the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g of prime of x if the second limit exists. Now if the second limit doesn't exist, then of course it's not going to work out. So there are some instances where this just won't work out for it. Okay? And this is L'Hôpital's rule. And all we can see is all you require to find this limit is to be able to find the derivative of both the numerator and denominator. So let me show you how we can use this to calculate what we saw before and prove now our expression. So again, we're going to calculate the limit as x approaches 0 of sine of x over x. Well, to calculate the limit as x approaches 0 of sine x over x, we need to know the derivative of sine x, and we need to know the derivative of x. We also notice that if we do substitute 0 in, it does give us an indeterminate expression. And we also know g prime at x doesn't equal to 0 on the interval for x equal to 0 other than when x equals 0. Okay, so the limit as x approaches 0 now is equal to derivative of sine x is cosine x, and derivative of x is 1. So now, if we can substitute 0 in, cosine 0 over 1, cosine of 0 is 1, 1 over 1 equals 1. And we get our limit that we were looking for. Easy and simple as that. Okay, let's try another one, or try a few other ones. So if you take a look at these, you'll notice that, first of all, if you do substitute the expression in the first one, 0, you'll get 1 minus 1 over 0 plus 0, which is 0 over 0. So that'll give you indeterminate form. But can we work out the derivative of each one of these? Well, you betcha. Derivative of 1 is just 0. Derivative of negative cosine x is positive sine x. And this is over. Derivative of x plus x squared is just 1 plus 2x. Well, I can substitute 0 in now. Sine 0 over 1 plus 2 times 0. You'll notice this turns out to be 0 over 1, which is just 0. So this limit just turns out to be equal to 0. Okay, so let's try this with our next problem. Again, if you substitute pi over 2 into the numerator, you do get 0. Just substitute pi over 2 into this denominator, Well, actually, you get infinity. You get infinity over infinity. So this turns out to be one of those other instances. Okay, so derivative of secant x, you got to remember this. Secant x, tan x, and derivative of 1 plus tan squared, tan x is just tan, I stated that wrong. Derivative of 1 plus tan x is secant squared x. Well, you notice the secant x can cancel with one of the square roots. So now this turns out to be the limit as x approaches pi over 2 over tan x secant x. Well, I'm going to continue to simplify this first. So tan x is just sine x over cos x. And we're dividing by secant x, so that means we're dividing by 1 over cosine x, which is multiplying by cosine x. So now I can cancel these two values out, cosine x and cosine x. And now I can substitute this pi over 2 in. And sine of pi over 2 just turns out to be 1. So now we can calculate some limits, but we need to know derivatives first. So this is one of the reasons why we couldn't use it in our previous problems that we dealt with before. I had to teach you derivatives first. Okay, so let's take a look at one last example here. This one's a little doozy. This one's a little bit more fun. So I'm not sure if you remember this limit. The limit as x approaches infinity of 1 plus 1 over x to the exponent x. But this turns out to be the value of e. This is Euler's number. Okay, well, we're going to do a little bit of rearranging and practice so we can do this. So first off, please realize that the natural logarithm of 1 plus 1 over x to the exponent x, notice I'm using natural logarithm because we have a x in a base and an x in the exponent. And in the past, we only knew how to find derivatives of these kinds of things using a natural logarithm or logarithmic differentiation. So this is equal to x times the natural logarithm of 1 plus 1 over x. Now another part of this, in order to use L'Hopital's rule, it's got to be a fraction. Well, right now this expression is not a fraction. So if I change it, so this natural logarithm of 1 plus 1 over x divided by 1 over x, then I have a rational expression. Okay? Now, I'm going to actually calculate the limit of this thing as x approaches infinity. How does that relate to this item? Well, we'll see. So now we're going to calculate the limit as x approaches infinity of this natural logarithm of 1 plus 1 over x to the exponent x, which is equal to the limit as x approaches infinity of 1 plus 1 over x over 1 over x. Okay, so if we do substitute infinity into both of these, you'll notice the numerator you get ln of 1, denominator you get 0. So ln of 1 is 0 over 0, indeterminate. Okay, so we have to verify that that works out first. Okay, so now I've got to work out the derivative of the natural logarithm of 1 plus 1 over x. And that's just 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is just negative 1 over x squared. Denominator is also negative 1 over x squared. That's derivative. Oop, I forgot the limit. Okay, well, I could do some canceling now. So this cancels with this one. So this just returns out to be the limit as x approaches infinity of 1 over 1 plus 1 over x. Okay, well, this limit as x approaches infinity, this value goes towards 0. So this overall limit just turns out to be equal to 1. So the question you must be asking yourself is, how does this work out? Or why does this help me? Well, now what we're going to do is we're going to look at this. So we know the limit as x approaches infinity of this 1 plus 1 over x to the exponent x. Well, that is the limit as x approaches infinity of e to the exponent natural logarithm of 1 plus 1 over x to the exponent x. Well, if we apply that limit that we had originally to that value, this limit to this exponent, so we're just finding out what the exponent approaches. So now this exponent approaches the value 1, which is just e. And now we've proven that the limit as x approaches infinity of 1 plus 1 over x to the exponent x is just the value of e. And thus concludes this lesson.